Thank you very much for being here. Today we're going to explore the concept of flatness in multivariable systems. And by that we mean systems of multiple inputs and multiple outputs. We will concentrate on the so-called class of square systems. By that we mean systems that have the same number of inputs as the same number of outputs. Not that the other class cannot be treated. It can also be treated, but there is not much interest in that particular area, at least from the viewpoint of flatness. And we will start with linear time invariant multi-input, multi-output systems. That will give us two representations. We will have a vector of outputs related to a vector of inputs. And in the frequency domain, this G is going to be a function of the complex variable S. So in this kind of input-output representation, we will have at least two options. One of them is the option of having a system written in this way, in terms of polynomial matrices. This will be square matrices, functions of the variable S. And that's the natural generalization of the input-output representation of linear time invariant systems, in which the output is related to the input by means of two polynomials representing differential operations on y and u. In the frequency domain, there will be just algebraic operations of the complex variable S acting on y and u. This will be one of the representations we will explore. A second one that we will explore is a representation called the pseudo state. This P doesn't have anything to do with that P. The pseudo state representation, Q of S u, and the output y will be a function R of S and C. This is called the pseudo state representation because this equation sort of resembles the state equations, and this variable C will determine the output in the frequency domain in a linear fashion through a matrix R. So this will be the two basic cases that we will deal with in multivariable linear systems. And then finally, something like this on its own, it also has interest, because this form, to learn how this form can be put into this form, requires a special kind of factorization. And of course, if the matrices here are well defined, this form is equivalent to this one. But this one is not always feasible or even useful to put in that form. But these are basically the three major forms of which the theory can be applied to. And flatness has a special meaning in each one of these representations. And then finally, we will resort to the state space representation, which is very popular, in which we have an input to state representation by means of matrices, in which B is a matrix of n rows and m columns. And the usual assumption here is that B is a full rank matrix. That means it's equal to the rank of B is the number of inputs. U will belong to the m-dimensional space, and X will belong to the n-dimensional space. So for this, the concept of flatness is very useful is very direct to be applicable. In these representations, the applications are somehow a little bit more difficult to encounter in practice. But of course, many systems can be represented by either these three types of models, and it's only that this being more popular, you find many more examples as a direct linearization of nonlinear multi-input, multi-output systems. So we'll spend some time in visiting what the concept of flatness means in each one of the cases. The first one we will treat is this, which is a direct generalization of the one we already had in terms of polynomials. And in that representation, we got the transfer function representation by which we could establish controllability in a very simple manner. This system is controllable if and only if these two matrices are coprime. They don't have common factors different from 1 or constants. So this is a program, and we will try to illustrate with examples each portion, and hopefully that will put us in the right path to obtain the generalization to multi-input, multi-output systems in the nonlinear system case, which is the most relevant of cases. As you will see, the concept of flatness applies very naturally to any representation of the multiple input, multiple output system that we laid out in the blackboard. So the amount of applications is interesting because multivariable nonlinear systems are very much in use in academia and many other practical problems, and their linearization just coincides with the state space representation, and that is particularly important then to explore how to obtain the flat outputs in a multivariable system, even if it is of the linear time invariant case. So this is a program. And historically, multiple input, multiple output systems were very difficult to treat by means of frequency domain techniques in the 50s and 60s, probably mainly in the 50s. Chemical engineers were very much acquainted with multiple input, multiple output systems in transfer function form using matrices. The only problem there was to generalize the classical results of linear system theory to their cases, especially because many of those models that they had delays in them. They were not easy to represent in any other way. State space was just beginning to emerge, and therefore, when the time was right, the generalization of the state space approach to multivariable linear systems gave people an opportunity to try to link whatever was known at the time of multivariable classical systems with the state space representation. So it was one of the justifications of the state space to be able to solve problems in a rather different way than what people were doing in the chemical industry, basically, for process control and so on. So the theory was very much visited by many researchers, and probably the biggest breakthrough that came in the 70s was the invention of the geometric theory of linear systems, which completely solved in a conceptual manner, of course, the decoupling problem. And that already there triggered also interest in the possibilities of extending that theory to nonlinear systems, and that was basically the task of the 70s and 80s with great academic success. So let's start with the matrix polynomial representation of multiple input, multiple output systems, in which you have the same number of inputs as the number of outputs. So this is the case of square systems, and they are useful enough to represent a number of practical examples. So in this polynomial matrix representation, the matrix Q is assumed to be non-singular. That means it is invertible in the complex domain, so that you can bring the inverse to the left of P and say that Q inverse P is sort of the transfer matrix of the whole system in terms of an input-output representation. If the determinant of Q were not zero, if this matrix were singular, then obviously it is because two or more rows of that matrix are linearly dependent, or they have factors in the complex domain, binomial or whatever factors, that will account for the singularity of the determinant of that matrix. If that were the case, then in the null space of Q, somehow you have rows that, in combination with these variables, will produce a zero as an outcome. Therefore, that means that some variable C will produce differential equations, or will satisfy differential equations by themselves. And that idea is the idea of a lack of controllability. So what we're looking for in this representation is the generalization of the notion of controllability to systems described by polynomial matrices in that particular framework. So the generalization will be some kind of lack of common factors between P and Q. That is the general idea, because that was useful for the single input, single output case. Only that here in the multivariable case it has a special name. Let's give an example of a linearized system, and this system actually represents the linearization of an orbiting satellite around the Earth. It's a very simple model that comes from a nonlinear model that is very well known. And you have two control inputs. One of them is aimed in the tangential direction of the orbit, and the other one makes the system go up. The tangential direction will produce motions that can make the satellite go to a higher orbit or to a smaller orbit, and the other one can change the radial, the tangential thrust and the radial thrust. So this system is a linear system. It has two states, C1 delta and C2 delta, or two variables that might qualify as state, and two control inputs. It turns out that you can write it without much effort by taking a Laplace transform. You can write it in polynomial matrix representation, with the advantage that in this particular case, the matrix Q is the identity matrix. So that system is evidently in the polynomial matrix representation. And of course we can take the inverse of this and bring it to a 2x2 system with 4 transfer functions or 2 transfer functions describing the system. But this system is controllable. In some sense it's very easy to see from here, intuitively, that the system is controllable. The highest derivative of C2 is being controlled by U2, and the highest derivative of C1 is controlled by U1, and the rest is interaction between the states. So in some sense, the possibility of inverting this matrix will be crucial, and the possibilities of having no common factors between these two matrices, and we will have to be precise about what we mean by those common factors. This representation is nice. It corresponds to what we're studying, and all we need to establish now is the controllability for that kind of representation. First, let's introduce a simple definition. If you have a square matrix P, we will say that P is unimodular if its determinant is a non-zero constant. So you have a polynomial matrix, you compute the determinant, and you get as a result a constant. That is a very interesting class of matrices, because normally you think that you have an n by n matrix, the determinant has to be the product of a bunch of polynomials, and all of a sudden all those products and sums of polynomials or sums of products of polynomials will collapse to be a constant. Well, that matrix is called unimodular if that happens, and it's very often the case in real systems. So if P is unimodular, in a sense, P has a matrix inverse which is also polynomial. This is even more difficult to assimilate in the first instance, because you think of a matrix, n by n matrix, whose inverse doesn't contain any polynomial in the denominators. It is because the determinant somehow has to be constant. So the inverse of this matrix is also a polynomial matrix. So the class of matrices that have to be available for the system on the right, playing the role of P, is a very special matrix. It has an inverse which is also a polynomial matrix. So if P is unimodular, if there exists some matrix R such that RP or PR is the identity, and in the case of R being an inverse on the left, is called the left inverse of P. And if R can lead you to obtain the identity by multiplying on the right, R will be called a right inverse of P. But the right or left inverse is also a polynomial matrix. For instance, this matrix, which is a square matrix, it's a polynomial matrix. Each entry is a simple polynomial, in this case of order 1, each one. If you compute the determinant of this, you will get -1. So the presence of S is cancelled in the determinant, and what you get is a constant, which is a non-zero constant. So that matrix is unimodular. And if you compute the inverse of that matrix, you will see that this is a matrix like this, 2 by 2 matrix, but with these coefficients or these polynomials in the diagonals rather than these ones. And that's kind of very interesting, because multiplying by the inverses on the left, and we will see that also on the right, we don't abandon the class of unimodular matrices. And this is going to be a natural candidate to be the right-hand side of our system representation, because you know that that matrix sort of plays the role of a constant. in the sense that the determinant of that matrix will be a constant. In this case, this matrix has determinant equals to -1. So the things that we said for left inverses of unimodular matrix P also apply for the right inverse of the unimodular matrix P. So if you have a unimodular matrix P, either a left inverse becomes also a right inverse. For instance, let R be the left inverse of P. So the product of these two polynomials is the identity matrix. If we multiply this identity on the right by, let's say, R again, we will get this triple of matrices C, RPR equals R. But if R is invertible by inverting this R over here, you will get that PR is equal to the identity. And R will be invertible because its determinant is a constant. It's a unimodular matrix. So anything that was a left inverse of P is also a right inverse of P. So it goes both ways. And the determinant will always be a constant. In this case, it will be the determinant of the product of those two matrices is just 1. So in the previous example, if you take P as this matrix, it is easy to establish, as we did already, that PR is equal to the identity, and RP is also the identity. So the left inverse is also the same as the right inverse. So any left inverse qualifies as a right inverse because of this development. So unimodular matrices are very nice because they are sort of closed in the set of all matrices that have constant determinants. The product of two unimodular matrices is also unimodular because the determinant of the product is the product of the determinants, and since each determinant is a constant, then the product of constant is a constant. Therefore, the product of two matrices is unimodular. Of two unimodular matrices is unimodular. For every unimodular matrix there exists an inverse, which is a left or right inverse, which is also unimodular. So, and we're talking about group operations here that are satisfied by unimodular matrices. Of course, there is an identity element in the set of unimodular matrices. The identity matrix itself is unimodular, and therefore you have the existence of a neutral element, and the operation of products of unimodular matrix is associative. Therefore, this is the group of unimodular matrices. So if we have two matrices, they are said to be left coprime if they have no non-trivial left or right common matrix factors which are not unimodular. For instance, a scalar factor is important not to be confused, because of course you can take out a scalar factor and you say this scalar factor I multiplied by the identity and I still get the same thing. Therefore, this scalar factor spreads out in the diagonal of the identity matrix, and that qualifies as a factor. Well, we're not allowing such a case. So the condition for this to be left coprime or right coprime is that they have no non-trivial left common matrix factors, which exclude, of course, the scalar factors, the so-called trivial factors. So two square polynomial matrices will be right or left coprime if and only if they will satisfy the Bezout identity. For instance, if P and Q are left coprime, then you can find matrices S and T such that PS plus QT is the identity. So the same property that we had in scalar polynomials for them to be co-prime was the satisfaction of the Bezout identity for a pair of new polynomials. Here the case is similar. If we have the matrices P and Q, and if they are left coprime, then that means that we can find right matrices S and T multiplying on the right to those matrices, and the result of this, the sum of these products will be the identity. So the same thing that we say for the left coprime, we can say for the right coprime. A and B are two polynomial matrices. They will be said to be right coprime if you can find matrices M and N such that when multiplied on the left of the matrices A and B, the sum of those products becomes the identity. And that's the Bezout identity being satisfied by factors on the left for the right coprimeness or on the right for the left coprimeness. So it's very, very similar to the single input, single output case in the sense that now coprimeness generalizes to the idea of matrices. And constants that were the preferred numerator of a polynomial, of a matrix, of a transfer function representation of a linear single input, single output system, it will become here the presence of a unimodular matrix in the right-hand side of the representation in terms of polynomial matrices. So it is kind of parallel, but this, of course, is more general and a little bit more complicated, because finding these factorizations sometimes requires special software, because the amount of equations that you have to solve becomes large pretty quickly, depending on the degrees of the polynomials in the P and Q matrices. If that degree is significant, then you have a lot of equations to solve. So what does this mean in terms of controllability? When you have a representation of your system in terms of this input-output form, in which you have a control and output variables in the same number, this system will be said to be controllable if P and Q are left coprime. This is the generalization. The controllability will be completely equivalent to the coprimeness of these two matrices. But since in matrix theory we have to distinguish between right and left coprimeness, we will say that the P and Q, if they are left coprime, then this system is controllable. There is no common factors, which are non-trivial common factors between P and Q, except those which are trivial, which are the identity and probably some constant that we're not regarding as a true factor. So if that is the case, then we can have a representation of this system in a very nice manner in terms of the coprime representation. If these two matrices P and Q are left coprime, then we can always find a matrix A and B multiplied on the right which give you the Bezout identity, and that is interesting, because then we can decompose this system in the following manner. If we let CS be represented as A times C of S, and E of S be represented as B of S times C of S, the existence of that vector C is guaranteed by the coprimeness. Therefore, we will say that two systems are left coprime. This is called the right coprime representation. Remember, Q and P are left coprime. That means there exist matrices A and B that, when multiplied on the right for P and Q, give you the Bezout identity. And so if we multiply the Bezout identity by this vector C, you will get Q B C equals to C. Multiplying this relation, this identity on the right by the vector C, you get PAC plus cubic C equals to C. So this is very, very reminiscent of this representation. If we let this to be U, P times U has to be Q times Z. So in essence, P times U plus Q times C will be there, and we will call ASC the right coprime representation of U, and we will let B times C be the right coprime representation of C. So moreover, this C is a vector of the same dimension of U and C, and therefore you have a nice decomposition of your system. And this C will play an essential role, and this C will play an essential role in the system description, because what it says is that C is a vector of elements, the outputs, that can be put as a differential, as a set of differential expressions on the components of C. And that U is a vector of components, of M components, in which each component can be expressed as a differential polynomial in the elements of C. Because this B of S is the transfer function, is the frequency domain representation of a differential polynomial on each one of its entries, and each one of its entries. So flatness naturally emerges from the coprimeness of the matrices involved in this representation, and it has the unique advantage of being explicitly brought out by means of Bezout identity, thanks to the fact that two left coprime matrices have a right coprime representation. And that will define flatness in a sense. So we go for the formal definition of a flat output in MIMO systems. A square system will exhibit a set of outputs Y, which is m-dimensional, and this system will exhibit Y as a vector of so-called flat output if it satisfies the following conditions. So in this representation, when can Y be considered to be the flat output? Well, for that representation, Y will be the flat output if two conditions are satisfied. First, the dimension of Y is equal to the dimension of U. And second, the components of Y do not satisfy differential equations by themselves. This is an independence condition of flatness. The flat output cannot satisfy a differential equation by itself, in which I struggle through the system equations, and I find that this output Y can satisfy a certain differential equation which is independent of U, in which U doesn't appear explicitly. So that cannot be a flat output, because that particular set of components of Y are uncontrollable, are non-controllable. So that means that the system has a subsystem which is completely uncontrollable. So these two conditions are very important. The dimension of the output has to be the same as the dimension of the input. Second, the components of Y cannot satisfy differential equations by themselves. And third, all system variables can be differentially parameterized in terms of y. So y is a flat output, and for that we will have the following result. If you have a square system of this form, and it admits as a flat output the vector of outputs, which is here has the component C1 through Cm. This system will admit C, the vector C, as a flat output vector if and only if the three following conditions are satisfied, which are equivalent to the previous one. The system is controllable. That means C cannot satisfy a differential equation for itself. P and Q are left coprime. Well, this is the definition of controllability. P and Q are left coprime. That's equivalent to being controllable. And second, the matrix P is unimodular. If those two conditions are satisfied, then the system is flat, and the flat output corresponds to the output, the actual output of the system. Of course, we still have this possibility for later on when we have a different representation. We will find a flat output when the flat output is not the output y of the system. And in this case, this corresponds precisely in the monovariable case when you have P times y or times C, let's say, equals Q times U. If this matrix is constant, then C is the flat output. Remember, the flat outputs have transfer functions in which the numerator is always a constant. This is the distinctive characteristic of the flat output in the frequency domain. Whatever you do with the variables, if you come up with a variable that has a transfer function related to the input, and that transfer function happens to have a constant numerator, that's a flat output. And in multivariable systems, having a constant numerator is not always possible. So what that idea generalizes to is the fact that the matrix P will be unimodular. And that means the determinant is a constant. That's as far as the analogy goes. The determinant is a constant. And if you find that in your system you manipulate your equations until you get a representation like this, and P is unimodular, its determinant is constant, then the flat output is C. As long as C doesn't satisfy any differential equation, that means that Q has to be full rank. Q has to be invertible. But that's guaranteed somehow in many systems. In many systems, this matrix is well known. Any questions? So the parallel is the analogy is rather nice, but of course the generality of the multivariable case forces us to consider the appropriate generalizations of the things we have in the single input, single output case. And those generalizations pertain to the coprimeness of matrices. Coprimeness here means that you can have left or right coprime matrices that satisfy the Bezout identity. If the P and Q are left coprime, that means there exists A and B that multiplied on the right produce the Bezout identity on P and Q. That means P and Q are coprime. By inspection, you can find that P and Q are coprime if they don't have any common matrix factors. If there is a matrix that you can factor out from P, and let here a matrix P0, and you can do the same with Q, and that matrix is common factor of the two, then that means the system is non-flat. So this is the natural generalization of flatness to multi-input, multi-output systems in the input-output representation where matrices Q and P guarantee the controllability of the system. That means the left coprimeness of Q and P is the condition of controllability, which in the CISO case is very very simple. Well, we can prove that. By that we can proceed by contradiction. Let's assume that C qualifies as the flat output of the system. And contrary to what we want to prove, that the two conditions are valid, we will assume that these conditions are not satisfied. If we get a contradiction, it's because our first assumption is wrong. So C wouldn't be a flat output. That's how the contradiction goes. So suppose that C is a flat output, but that none of these conditions are satisfied. I mean, the system is, P and Q are not left coprime, and P is not unimodular. If we have those two conditions, then if the matrix, then the matrices Q and P have a non-unimodular greatest common left divisor matrix. That means they will have some common factor, and this common factor will not be unimodular. That's what we mean by a non-trivial factor. We cannot get out of those two matrices a left factor that is not unimodular. So let's denote by LS that factor. That means that in the right coprime representation, Q will have a factor of indicated by L of S. So you will be able to decompose Q as the product of L of S and Q0, and L of S will not be unimodular. And P will also have a common factor. That means L will also be an integral part of P and multiplies a matrix P0. With, of course, Q0 and P0 would be coprime in this case. So if that is the case, because L is not unimodular, then we can establish that Q0 times C minus P0 times U will be, as we put here in the Bezout identity, a matrix C, because the right coprime representation of C and U will be of this sort. So we will be able to do that. But in this case, L will annihilate C. If you multiply L by C, you have LQ0 times Z minus LP0 times U will be 0, because LC has to be 0. And that is precisely the representation. Q times C is equal to P times U that we had in the beginning. Only that we put it in the left half part of the equation, to bring out the fact that the existence of a common factor which is non-coprime, in spite of the original matrices being coprime, but the product of a common factor will destroy the issue of controllability, because that factor there, which is non-unimodular, will be able to produce a 0 on this vector C, which is responsible for the right coprime representation. If we do that, then evidently C is satisfying a set of differential equations by itself, one equation for each row vector of the matrix L, and therefore C is not controllable. Therefore, the initial assumption was wrong, and it consisted in saying that we did have a flat system, but none of the two conditions were valid. If none of the two conditions are valid, P and Q are not coprime because they have a non-unimodular common factor on the left that you can extract, and the Bezout identity will tell you that necessarily there exists an annihilating matrix of C which will reproduce the system equations. And that means that C cannot qualify as a flat output either. So we have the result that controllability is totally equivalent to the existence of a flat output vector. Now, for the second part of the proof, given that C is the flat output, then there will exist a differential parametrization for U and C, as we had in the right coprime representation. So U will be some matrix times C, and C will be some matrix times Y. And therefore, the flat output will satisfy this with Q and P0 free of any multiple. If Q and P0 cannot be made free of that multiple, then when you multiply it on the left by that multiple, you will get that C satisfies a differential equation by itself, and that cannot. That's a contradiction to the assumption of the existence of a flat output. So in that case, C would not qualify as a flat output, and because its components satisfy a set of differential equations in which the control is not present, is not explicitly present. Therefore, let's probably make some examples to clarify the ideas. If you have an input-output representation of that, of course you immediately see that this is a unimodular matrix. The other thing would be, is this matrix right coprime or left coprime to this? Of course, it has to be left coprime because there's no common factors. There's not an entire matrix that factors out of this matrix and factors out of this matrix, which are the same. Therefore, this system is controllable. The two matrices are left coprime, obviously, and the one on the right is unimodular. So the inverse of this matrix is also a polynomial matrix of order 0, and the determinant is constant. So in this case, Y would be the flat output. You would have two flat outputs, and of course, the inputs are differentially parametrized by those two flat outputs immediately. So that's probably a very simple case. Let me go back to the satellite model. This is a very nice satellite model, a nonlinear model in which you have the dynamics of the radial dynamics and the tangential dynamics. The angular dynamics is represented by these two matrices, and the radial dynamics is represented by these two matrices. And you have radial control. You can go up and down, and you can make a change in the angular description of the evolution of the satellite orbit. So you have four distinct state variables, two distinct controllers, and the system is nonlinear. Here x1 is the distance from the center of the Earth, x2 is the radial velocity, x3 is the angular displacement with respect to an orbital reference, and x4 is the angular velocity. And the controls are, in one case the control is a force, and in the other one the control is a torque. You can linearize this system around an orbit which is at a fixed height with zero velocity. That means the orbit is stationary with respect to the center of the Earth. It's always at the same distance. The angular velocity the angular position is increasing in time with a constant angular velocity. The angular velocity is constant, the angular position is growing linearly in time. If in that model you impose the condition that the square of the angular velocity is times the cube of the radial orbit is equal to k, this is a very well-known condition from the classical physics, from classical mechanics. When the cube of the radial orbit times the square velocity of the square of the angular velocity is a constant, then you have a stable orbit. And that's a very well known. So you have a state space representation of your system in terms of your inputs and your outputs, and your outputs in this case will be the radial position and the angular position, and the states are going to be the radial position, the radial velocity, the angular position, and the angular velocity, and the controls is, one of them is a force, the other one is a torque to change the orientation of the spacecraft. When you take Laplace transforms, you get this, which we had already seen. So that system is controllable. Why? Because this matrix is unimodular, and And of course, y does not satisfy a differential equation by itself, which is independent of u. So this matrix is R co-prime, and the one in the right is unimodular, therefore the system is flat. So only two conditions, co-primeness and modularity, and unimodularity, to check for flatness in input-output representations. And in that case, y will be the flat output. And that's very useful, because from here you can immediately propose a control strategy to control each one of the degrees of freedom, which in this case is the radial and the angular orientation of the orbit. So x1 and x3 are the flat outputs. They have a very physical meaning. Another example, just for fun. This is a rolling mill. This is a lateral view of the rolling mill, and this is an upper view of the rolling mill, in which you have a slab of material that goes into the mill, and the purpose of this mill is to squeeze that surface in order to control the width when the steel is hot. But if this is probably a cold rolling mill, because it can also do the same thing when the steel is cold, if you have enough pressure to exercise on the slab of material. So this system has many outputs, many inputs. In fact, you have m inputs, and at each point you're measuring the thickness of the material, therefore you will have as many inputs and outputs. This is a square system, but the dynamics is very simple. It's a first order dynamics acting on each component of y, and on the right you have a matrix which gives you the interactivity in the system. There is a system of sprays that is acting on that material, and as you progress into the space of this model, then you have different interactions which are sort of geometrically going, and you have each spray is acting on each particular portion of the slab, and the rest comes from the lateral influence of the other sprays affecting the first, the second, etc. So alpha means a level of interactivity. Of course, the ideal thing would be to have alpha 0, but that means it's not possible in practice. It's very expensive in practice. So you do have some interaction from the sprays, which are neighbors of each one of the portions of the slab that you're interested in controlling. So the number of sprays have some interactions. This matrix M is the interactivity matrix, but this is a constant matrix. The dynamics of each spray system is the same, very similar. They have the same time constant, and they are controlled by U. So that system is very simple, but you can represent it like this. This common factor can be spread out into the diagonal of identity matrix, and each one of them represents an independent dynamics for the components of Y, but the interaction comes in M. And M, fortunately, is an invertible matrix. M is constant, and therefore it's unimodular. This matrix is unimodular, and of course these two matrices are coprime. Are left coprime because this only has one factor, which is that, and this doesn't even have the possibility of having that factor. So that system is flat. So the flat outputs are just the Y's. And you can set up a very nice controller for that. You invert that matrix, that first order dynamics, and you get an inverse like this. This matrix is perfectly invertible, and you can obtain the parametrization of the control inputs and the reduction by means of this transformation to a set of independent integrators. So you can put a proportional integral controller, and by doing that you will have the actual controller. You have a bunch of of differential equations of first order, each one controlled by an auxiliary control input V. So here you have that your multivariable system decomposes into single unidimensional subsystems, which are independent of each other at the level of this auxiliary input V. And you specify that V as a proportional integral controller, and you close the loop and find the actual control U by means of this decoupling matrix that sort of inverts the interactivity between displays, and this is your control law. And with that control law, you will have a very nice performance. After you do some simple design, you will see that you can actually control and sustain some disturbances along the way. So here at each one of these little rows you have one control problem. All of them can be simultaneously solved because of the flatness of that particular output, and sustain disturbances which recover relatively quickly. So those are the simulation results, and we have robustness. When you don't have any perturbation, then you have a nice smooth stabilization, and when you have disturbances, constant disturbances, you can see the effectiveness of the control. Questions? How about generalizing that to discrete time systems? Yeah, that's something that has to be done.
This is called polynomial business. This was under linear system theory in the 80s.
Yeah.
And Professor Hunt has his own version of this. And he parameterized the Q and P and matrix with the 1 S square and so on. So it's already in the kind of very nice
decoupled manner.
Yeah, very nice polynomial form.
Mm-hmm.
And that polynomial form corresponds to the canonical form.
Yeah. Brunowski form. Yeah.
So he made some original contribution to this. So
yeah.
I think there's possibility of using his representation in polynomial form and get to the combine it with the flatness.
Yes, of course. That's a nice project for somebody.
Yeah.
Because it rescues something that has been long forgotten or not very much advertised. But
right.
it is true. I mean, everything, we can see that everything's related.
Yeah, so from your P and Q matrices, you can go one step further, put it in the standard canonical form, and maybe derive a precise output from there.
So he had a canonical form for P and Q?
For all polynomial matrices.
Decoupled?
Well, yeah, he studied all this linear system problems in his own version.
Yeah.
So he has his own book, but the book is in Chinese.
Unfortunately.
He taught it for over 10 years. He and Professor Xu. And Professor Xu came here in 1996, and he presented his result to us. This polynomial approach. So it's could be very profitable to combine that with this. Could be.
Yeah. But did he do it in the context of ADRC or something?
No. This is
independent.
But this is related. In 1979, he came up with this canonical form for linear and nonlinear system in cascade integral.
Okay.
Yeah. So he's very consistent in his different fronts of research in the polynomial in linear system theory based on polynomial approach. He has this very nice canonical form. And that I think ADRC formulation is influenced by that conceptualization.
Of course. Well, it would be nice to have somebody look into that and rescue the main ideas. There may be more than flatness to it. Yeah. Many other things might become transparent from that formulation, and it's a pity that very few people know about it.
It's a pity. It never published in English literature.
Yeah.
But it's a well-established textbook.
Yeah. Okay, good. That gives us a project. How about doing it for discrete time system?
Yeah. That can be done.
Okay. The other representation we have is in terms of transfer function matrices. They're more complicated because they're matrices in which each entry is a proper rational and the whole matrix G is a matrix of rational proper rational transfer functions, and therefore G is kind of complicated, have different numerators and denominators. So how can we establish the existence of a flat output for this multi-input, multi-output system in which Y and U have the same dimension? You have M components of the output vector and M components of the input vector. And of course G is then a square matrix of rational transfer functions. Now, if that square matrix G, I mean, let's say that it takes values in the space of n times m matrices. If you can put this G, you can factor this G as Q inverse P. Of course, you get back a polynomial representation, because when you substitute this there, you get QY equals PU. Was that the same I was using? No, I was using it the other way around. Sorry for that. So if you can factor this G as the product of two polynomial matrices, one of them is P as polynomial, and the inverse of, and this Q itself is polynomial, but its inverse is any matrix with proper rational transfer functions. Well, when you invert that, you will obtain back a polynomial matrix. Then this representation coincides with the original representation. And in that case, we would have to check that this possibility of factoring out G corresponds to left coprime matrices Q and P. If that is the case, then we say that G has a left coprime factorization, and we will denote this factorization by this. I'm sorry that I was using Q and P. I should have used P inverse Q to conform to that representation, but oh no, it's the same. No? Oh, it's the same. No, it's the same. So we're fine. So if you can do that and you obtain two left coprime matrices, then G has a left coprime factorization in terms of Q of P. Therefore, all you have to check now is that P has to be unimodular. So we will say in general that if a square matrix G is a matrix of rational transfer function, if it can be written as a product of A times B inverse with A and B being right coprime, then G will have a right coprime factorization. So this is a left coprime factorization, this will be a right coprime factorization. The way to remember that is in the left coprime factorization, the inverse is on the left, and in the right coprime factorization, the inverse is on the right. Then when you have this right coprime factorization, it's very easy to relate that representation to the previous one. And flatness would still apply. So if you have a system which is a square in rational transfer matrix representation, where G is a non-singular matrix, this is the first condition. And the second condition, the transfer functions integrating each element of G has to be a proper rational transfer function. That means the numerator never exceeds, the degree of the numerator never exceeds the degree of the denominator. This is a proper rational transfer function in the complex variable S. So in that particular representation, we will say that the system is controllable if and only if the matrix G admits either a left or a right coprime factorization. This would be a left coprime factorization, or else, I believe, a right coprime factorization, in which you have the representation of in terms of polynomial matrices. B is a polynomial matrix and A is a polynomial matrix. G is a matrix of rational transfer functions. The inverse of B will produce the denominators that will multiply by A will give you transfer matrix representation. So if you have a right or left coprime factorization of the transfer function, then you are back in the original formulation, and now we can establish flatness on this by saying if these are coprime and this is unimodular, then you'll have Y as a flat output. So in the frequency domain, it's not very difficult. The only thing is that these coprime factorizations are not easy to do by hand, especially when you have a 5 by 5 matrix or something like that. So you have to use software somehow. Symbolic manipulations that bring you the left or right coprime factorization of the given matrix. If that can be done, then you're in a good track to obtain flatness and use it for practical purposes, but that's not always easy. I'll give you a simple example, 2 by 2 example of physical nature in which you can do this. You have a heat exchanger, which is very well known to mechanical engineers. You have a fluid with a certain temperature that visits this exchanger, and you have another fluid going probably in the same or the opposite direction, it doesn't matter, that receives heat from the first one, and this interchange of heat will result in a change in temperature of one of the in both of the fluids. And the dynamics in terms of there is a cold water inflow and there is a hot water inflow, and the idea is to interchange. The temperature always goes from the hot to the cold. So to warm up the cold water is one of the purposes. The other one is probably to lower the temperature of the hot water stream. So if we denote by T sub C, is this well seen in the camera? If we denote, otherwise we can switch to the, can you see this? Okay. So what is the dynamics of this system, and what are the controls? The controls in this case is the input temperatures of the cold and the hot water. C will stand for cold and H will stand for hot. So the input temperatures TH and TC will be somehow the inputs to the system, and the state of the system is just the temperature at the exit of the interchange, the heat exchanger. T sub C and T sub H will be the two temperatures that will conform the state of the system. And of course there are physical laws describing the interaction or the gradient of temperature between the two things by means of, in this case, this simple model, a constant factor, multiplying the inputs time the temperature and the cold one for the hot one, and the control inputs TC and TC and TH will be the states, and TCI and THI will be the inputs. So you have a nice simple system in which there is a lot of interaction. In fact, the whole idea is to make that interaction valid for practical purposes. So you have a state space representation in terms of all the system constants, and the state is just the temperature of the cold stream and the temperature of the hot stream, and the controls U1 and U2 are the input temperatures of both independent streams. So when you do that, you can simplify that system because there is a lot of symmetry there and a lot of constant that can be simplified, and you can write the system because it has basically similar dynamics, only that divided by different values of the volume, and the volume can be made equal, and therefore we can simplify the system to a very standard type of state representation of those interchanges. So you have a diagonal matrix indicating that the system is diagonally stable, and you have some interactions, and then you have the influence of the control inputs on each one of the components of the state, and the output is just the temperature at the interchange surface. So when you do that, you obtain the transfer matrix representation, something like this. You have two factors here, a nice polynomial matrix. And of course, in this case, it's easy to see that that matrix of transfer function representations will have a factorization, will have a left coprime factorization. The left coprime factorization in this case goes like that. If you invert that matrix and multiply it by this, you will have the same G that we were describing upstairs, up here. And you also have a right coprime factorization. So G of S can be put as this polynomial matrix times this diagonal polynomial matrix also. The inverse of that diagonal polynomial matrix will conform in this product as a right coprime factorization of G, and this will be a left coprime factorization of G. So this is an example in which everything works fine. And here you can, by inspection, you can obtain the left and right coprime factorizations. But it's not always easy. For 2x2 systems is kind of simple. So the theorem goes like that in order to characterize the flatness of this transfer function matrix representation. Square system in transfer function matrix representation is flat if and only if the system is controllable. And controllable means that you will have either a left or right coprime factorization, and therefore back to the original representation in terms of P and Q. P and Q are left coprime or right coprime, and the unimodularity, well, the flatness of the system will be guaranteed from the controllability of the system. So if the system is flat, then you have a vector which is independent. It doesn't satisfy any differential equation in its components. And that vector will differentially parameterize the inputs and the outputs. The inputs are U and the outputs are C, and this independent vector Y will be able to parameterize differentially by means of a polynomial matrix the components of the output and the components of the input. And A and B will be non-singular square matrices. So that means that Y is a matrix that is endogenously generated because it depends, is related to the inputs and the outputs. And moreover, when you invert that matrix, Y is a function of the inputs and the outputs by means of the Bezout identity. If you have that, then if A and B are non-singular square matrices, then you can find square matrices M and N so that you have a left coprime representation of the output in terms of the inputs and the outputs. So Y is endogenously generated by the inputs and the outputs through polynomial matrices. This M and N are part of the Bezout identity. These are polynomial matrices associated with A and B. So M and N on the right or the left can reproduce the Bezout identity as left or right coprime factors with B and A respectively. So Y is an endogenous generated variable because it can be computed in terms of the only system variables, which are the inputs and the outputs. And with the help of the Bezout identity, when you substitute this left coprime factorization of the inputs and the outputs, then you will see that the flat output Y satisfies the Bezout identity times Y itself. I mean, this sum of matrices times Y, but because of the Bezout identity, this will be the identity, and that will reaffirm you the fact that Y is the flat output. So a flat output is an endogenous variable that can differentially parameterize the inputs and can differentially parameterize the outputs. Remember that A and B are no longer transfer function matrices. These are polynomial matrices. So A and B have rows which are only polynomials in the variable S. That means differential polynomials in terms of the derivative operator. Therefore, Z, the actual output of the system, is differentially parameterized by y, and u is differentially parameterized by y also. Therefore, y is a flat output, and moreover, a and b are coprime, and because they are coprime, they satisfy the Bezout identity, and you have left and right coprime factorizations of those matrices, and therefore you will have flatness. So that shows you that if that's not the case, you easily run into a contradiction. So the same thing we say for the right coprime, we can say for the left coprime, and therefore the theory is kind of dual. If you stick to one of the representations, you will be able to convince yourself that you can compute the flat outputs in either case by right coprime factorizations or left coprime factorization. And as an example, if you have a matrix of rational functions, then this has a right coprime factorization in terms of this matrix times the inverse of this diagonal matrix. This is easy to do in 2 by 2 cases, but it's not easy to do in a 5 by 5 case or 10 by 10 matrix. It's very, very complicated. But fortunately, there is a specialized software that allows you to do that computation. And if it can be done, it will give you the solution. The only problem is that sometimes the solution comes in terms of system matrices A, B, C, and D, and it's difficult to reinterpret back what they mean. But if the system is controllable, then it's flat, and you will have a differential parameterization of the inputs and the outputs in terms of those flat outputs. And y1, y2 will be the flat outputs in that case. Very simple generalization of the input-output case. And of course, you can verify the existence of the satisfaction of the Bezout identity by means of two non-singular matrices M and N, and you can compute them M and N with some pain, because you have to solve this sort of large number of equations with unknowns, 4 equations with 4 unknowns, or 6 equations, no, 2, 4, 8 equations with 8 unknowns, and you can find the factorization. So the flat outputs depends on the inputs and the outputs. The inputs are here, the outputs are here. Therefore, the existence of a flat output is a direct consequence of the controllability of the system and the coprimeness of these matrices, polynomial matrices P and Q. And the heat exchange, well, we already saw that one, right? Yeah. This is an example of how to compute that for this matrix G of the heat exchanger. If you get this factorization, we actually presented 2 of them. That factorization leads to differential parametrization of the inputs and the outputs, and therefore the system is flat, and y1 and y2 represent the flat outputs, which is actually the states, which are the most natural variables to be controlled. So that doesn't surprise anybody. Any questions? Because now we have to explore a little bit on something which is not also very traditional in linear systems theory. Basically, the program only examines single input, single output systems, but in multiple input, multiple output systems, the concept of poles and zeros is different. And this has to be well known in order to be able to handle flatness and the consequences of flatness, and the design procedure and non-minimum phase systems and so on is not so straightforward as in the single input, single output case. For multiple input, multiple output case, the concept of poles and zeros plays an essential role, and basically in determining the non-minimality of phase of the given outputs. Some of them might be non-minimum phase, and we have to be able to compute that. Is this something that's familiar to all of you? Poles and zeros of multivariable systems?
I did my master's thesis on this.
You did your master's thesis on this?
Yeah. So
Well, then I'll let you take over.
it's no longer relevant.
It's no longer.
People moved on. In the 80s, this was very hot.
Yeah.
But there was not much came out of this in terms of practical application.
Yeah. Well, here is very important because it allows you to tell to separate, non-minimum phase variables from minimum phase variables, and to show that the flat output doesn't have any zero dynamics. So the concept of poles and zeros is very relevant, and especially the concept of zero dynamics. The stability or not of the zero dynamics is important in that particular case. And this has to be done also for discrete time systems. So one basic concept is the so-called pole polynomial. The pole polynomial is a polynomial whose roots are the poles of the system. We have to be able to identify in either of the matrix representations of the system, either polynomial matrices or rational transfer function matrices, we have to be able to identify what is the zero polynomial. The zero polynomial is just a polynomial whose roots are just the poles of the system, of the whole system. And the zero polynomial, of course, is the polynomial whose roots are the zeros of the system. So we have to identify these two polynomials, zero polynomials and pole polynomials. The pole polynomial, which is the first one that is directly related to the stability of the system, the pole polynomial is characterized of a system characterized by the square transfer function matrix G, is the least common denominator of all minor determinants of G. So this is a non-trivial generalization of the case of single input, single output. In single input, single output, you just look at the denominator to find the roots of the polynomial in the denominator, and this will give you the poles of the system. But in multivariable, you have to take the matrix representation, the rational transfer function matrix representation, and take all the minors of the transfer matrix. There is a lot of them. In an n by n matrix, you have n square minors. The minor is the determinant that results from eliminating the column and the row that intersect at that particular element. So for each element, you eliminate the column and the row, and you're left with a smaller dimensional matrix, which is still square because you took out one row and one column. That matrix has a determinant, and you substitute that determinant. You form a matrix with those determinants. So when you have all those minors, you find the least common denominator of all these minor determinants of G. Each one of these determinants will have a numerator and a denominator. It's a product of a bunch of polynomials and rational transfer functions. And when you look at them, you have to be able to take what is the least common denominator of all the minors. That is the pole polynomial. And so the poles of the system are the roots of that pole polynomial. And the order of the system equals the degree of the pole polynomial. That is the true order of the system. It might differ from the dimensions of the matrix in the system. An example that we already saw. This is my transfer function matrix. Let's take all the minors. What is the minor of this? This one, so we put it there. The minor of this is this one with a minus sign. It doesn't matter, the minus sign, it's there. What is the other minor? The determinant itself. So you have three minors. And well, the minor of this is exactly the same. So this is repeated for this and this. This is repeated. This is the minor of this. This is the minor of this. This is repeated. And finally, the whole determinant is something like that. Now you look at the denominators of all those minors, and you take the least common denominator of all the minors in, and that will be the pole polynomial. In this case, you have 1 plus s, it's here with power 1, with power 2, you take the maximum power, it's the least common denominator. And 1 plus 2 repeats here, is with second order here, you take that. That's the least common denominator, this one, right? Because the product of these two without the squares would be a common denominator of these two, but it's not a common denominator of this one, so you have to take the squares. So that is the pole polynomials. So how many poles we have? We have 2 poles here and 2 poles here. That's 4 poles. And the system is only 2 by 2. Right? I mean, it has 2 inputs, 2 outputs. And you have 4 poles. Because the pole polynomial is 4th order. So that's a concept that's very different to single input, single output system. If you don't believe me, you ask Professor Gao and he will tell you. Another example. If you have these square matrices, SA and SBs are somewhere. The minor of this one is the same one, so you have 1 in 2 minors. The minor of 1 over S plus B is 1 over S plus A, so you already have there. The minor of this is this, you already have it there. And the determinant is another minor, so you have the product and you have this. Those are the minors, yeah. When you multiply this, you got 1 over S plus A squared minus 1 over S plus A S plus B. So you take out the common factor 1 over S plus A, you solve that, and you will get this is the minor. So what is the least common denominator of these factors, of these 3 denominators? Well, it's the one with the greatest power, which is repeated or non-repeated. So you have this. This is 3rd order system. It only has 3. In the previous example, we had a 2 by 2 matrix. The order was 4. Here, this is a similar matrix, very similar. 2 by 2 matrix, the order is 3, not 4. So it's completely different to the single input, single output case. The system is 3rd order. In the heat exchanger that we were examining, the minors are very easy to compute. The minor of this is S plus A divided by the other determinant. The minor of B is B divided by the other determinant, and so on. And the determinant is S plus A squared minus B squared divided by that. If you make a factorization, you get this. These are the minors. So what is the least common denominator? Well, S plus A appears, S plus A plus B appears here, so that's one factor. The other one is S plus A minus B. Therefore, the least common denominator is a 2nd order polynomial. The system order is 2. So I gave you 3 examples of 2 by 2 matrices. In the first example, the order was 4. In the second example, the order was 3. And now in this example, which is not very different, dramatically different from the other, the order is 2. So you never know until you compute it what is the order of the system. It doesn't go by saying, oh, this is a 2 by 2 matrix, the order is 2. It doesn't work. So you have to compute the minors and obtain the least common multiple of all the denominators in the minors. And that will give you the pole polynomial. The pole polynomial, the number of roots of the pole polynomial will be the order of the system. So very different to single input, single output systems. And the zeros, they are much easier to compute. The zeros of a square transfer matrix G are very easily defined. They are the zeros of the determinant of the matrix. So, but that's true when the denominator of the determinant is normalized to be the pole polynomial. So what you do? You take this matrix, for instance. We already saw what was the pole polynomials. And let's see, the determinant of this is the product of this minus the product of that, which is 1 over s plus a squared minus 1 over s plus a is 1 over s plus b. So, and when you put as a denominator the Pol polynomial that we computed, in this case was a third order polynomial, when you divide that polynomial, you will obtain something like this. This is the determinant of G, of this matrix. It has precisely the Pol polynomial is at the denominator of the determinant of G, because this is what we computed. So the zeros are the zeros in the numerator. There is no zero here because the numerator is constant. So there is no zero. So this is the trick. It's easy to compute because it's just the zeros of the determinant. But that has to be done with a qualification. That the zeros of the determinant when the denominator is the Pol polynomial. So you put the Pol polynomial and then you complement with whatever you need to make the denominator the Pol polynomial. And then the zeros will be the zeros in the numerator of that determinant. Very different. So in the heat exchanger, for example, this is a system transfer matrix. This was the Pol polynomial. If you take the determinant of this matrix, you will obtain this. And precisely this denominator is the Pol polynomial. So you don't have to force anything here in this example. But if you didn't have the Pol polynomial, you have to put it there and multiply by whatever is required to have this as the Pol polynomial. And in this case, there is no zero. So what do we understand by minimum phase or non-minimum phase systems? Well, it has to do with the stability of the zeros in the transfer function matrix. If the zeros are stable, then the system is, the outputs are said to be minimum phase. If the zeros are unstable, or one of the zeros is unstable, then we have to look for that instability tells you that the system is non-minimum phase. So in this case, it was very easy to define, for the CISO case, it was very easy to define the system zeros. And a system was minimum phase if the zero polynomial was stable, has all the roots in the left half of the complex plane. In a MIMO system, the case is totally different. A MIMO system will be called non-minimum phase if the zero polynomial has some of its roots, doesn't have to be all of them, some of its roots, at least one of its roots in the right half of the complex plane. That system will be a non-minimum phase system. So the zero locations for a system are highly dependent upon the parameter values. And we have an example, a dramatic example, which is kind of difficult, but it was a challenge that was placed in the internet to control that system because it is a non-minimum phase system. The problem, I don't know if you see it very right, you have a tank here from which you have two pumps. The first pump feeds this tank and this tank. And the second pump feeds this tank and the other tank. So the pump here pumps water into these two diagonal tanks, and the pump here feeds water into these two other diagonal. So there's a lot of interaction, and it's a nonlinear system. And you have two controls, and you have four states. The states are the level of the liquid in each tank. And the problem is to stabilize that or to follow a trajectory. So the system has a very nice structure. It's highly nonlinear because it's the square roots according to the laws of hydrostatics. The square roots will determine the rate of change of the growth of the level of the liquid in each tank. So you have 4 levels to control, and you have only 2 controls, V1 and V2. V1 controls the first and the fourth, and V2 controls the second and the third. And you have 2 outputs that you want to control. The outputs are the levels in the first and the second tank. You want to control these 2. But you see, this is perturbed by the fact that the other pump is putting water into this. And this is affected also by the other pump. And here you have valves, and these valves let some liquid flow at a certain fraction of the total flow. For instance, here we have a factor of gamma 2, and here gamma 2 or gamma 1 and gamma 2. That means that not all the flow goes to the tank, but only a portion of the flow goes to this tank, and the rest of the flow goes to the other tank. And these gamma 1 and gamma 2 parameters you can change. You know, they are static parameters, they are not the control parameters, but these gamma 1 and gamma 2 can have values between 0 and 1, let's say. They are positive, but the values vary between 0 and 1, and you can set them to be constant of different nature. You can set them equal or different. And the controls are U1 and U2, is the flow provided by the pumps. But only a fraction of the total flow goes to the first tank, and the rest goes to the second tank. And here that fraction is gamma 2, and the rest goes to the other tank. So it's a 4th-dimensional system, 2 inputs, and there is 2 outputs that we want to control. So it's a square system. And you can compute the equilibrium by setting all the left-hand sides derivatives to 0. You can compute the equilibrium points of the system. And they correspond to constant flows. You have V1 capital equal capital V1, and the second control V2 equals capital V2. You will obtain the heights of each tank computed in terms of the constant of the parameters of the system and the distribution parameters gamma, and the volumes of the tanks and everything. Though this is the equilibrium of the system. This is the height of each tank in equilibrium. It's a well-known function of all the parameters of the system, the volumes, the heights of the others, and so on. So we can linearize the nonlinear system around this constant equilibrium. And we do that, and we define the incremental variables C1 delta as H1 delta, and C2 delta as H2 delta. So that's the incremental height of the liquid level in the 2 tanks that we want to control the system, which are the tank 1 and the tank 2 at the bottom of the 4 tanks. Incidentally, some people in Spain put a lab with this example. And the challenge was, through internet, you could specify, almost in an automatic manner, you could specify the control law, I think in MATLAB code. This is my control law. And the system would test in the actual experiment your control law to see if you satisfied your objectives. So that was an online experiment that was offered to all the world who wanted to try the control laws to see how good they were in comparison to others. And they had one championed by themselves. So from the linear representation, you have this transfer function matrix. Some of the denominators are first order, some are second order, and you have all the numerators are constant, but that doesn't tell us anything. So let's compute the zeros, first the poles and then the zeros, to see what the effect of these distribution parameters gamma 1 and gamma 2 is on the stability of the overall system. So in simplified manner, this is the transfer function of my system. 2 inputs, 2 outputs. 2 outputs to control, 2 inputs to be controlled. all the numerators are constant, so it shouldn't be that difficult. So what is the pole polynomial? The pole polynomial is obtained by the least common factor of all the minors of the matrix. So one minor of the matrix is this one. The other minor of the matrix is this one. This is a minor of that, so this is another factor. The minor of this matrix is this one, so it will be there, and the minor of this element is this. So the four minors are there, and the determinant itself will be something like that, a little bit more complicated. So what is the least common factor of 1 plus s, 1 plus s squared, 1 plus s squared, 1 plus s, and 1 plus s4? The common factor is 1 plus s4, the least common factor. So the system is fourth order. Well, naturally, we had 4 tanks. We think that the system order is 4. But we should be ready for a surprise sometimes. The order of the system doesn't coincide with as we saw already in 3 examples. So we have the computation of the pole polynomial. Now we have to compute the zero polynomial. And the zeros of the transfer matrix is just compute the determinant. And when you compute the determinant, here, fortunately, the denominator of the determinant is already the pole polynomial. So we don't have to do anything. Therefore, the zeros are given by the roots of the numerator polynomial. And you have this very nice polynomial in S. When you solve for the roots, you get some kind of complex behavior of the roots depending on this distribution factors gamma 1 and gamma 2. And you can see that if gamma 1 and gamma 2 exceeds 1, then this term is negative, and the system subtract from 1. Therefore, it will never have a square root because gamma 1 and gamma 2 are positive and the sum is positive. When this is greater than, when this is 1, this is 0, and therefore you have minus 2 and 0 as the roots of the polynomial. But if gamma 1 plus gamma 2 is larger than 1, then the system is minimum phase because the 2 poles are maybe complex, but they have a negative real part. But if gamma 1 plus gamma 2 is smaller than 1, then the system is non-minimum phase, because now the two roots have a positive real part. So it's nice to control the system because it has a non-minimum phase internal problem. And one of the things we can do with that transfer matrix is to obtain the right coprime factorization. In this case, it can be done like that. This is the inverse of this matrix multiplied by that. This inverse on the right, you have a right coprime factorization. And with that right coprime factorization, the flat outputs are immediately y1 delta and y2 delta. So you can differentially parameterize all the variables, all the 4 states in the system and the 2 controls or the 2 outputs you are interested in regulating and the 2 inputs in terms of the flat outputs, which are y1 and y2. And when you do that, then you also might try the Bezout identity in order to compute the flat output from the inputs and the outputs. But that's not as useful as computing the flat output as we already did here. Yeah? So this is just to illustrate the difficulty in obtaining the matrices A and B that satisfy the right coprime factorization. So you have to put unknowns in all the elements of the matrix, and it's not easy to see what is the order of those polynomials should be. And this matrix should be a constant, but that's a fortunate guess. And even so, here you have a bunch of equations. These are very difficult equations to solve by hand, and well, that was done there. We obtained the polynomials, the components of the polynomial matrix, and that gives you A and B. And with A and B, now you have to solve this sort of Sylvester equation for all the unknowns in the polynomial matrices. And how do you have the solution of those linear unknown coefficients in the matrix factorization? And you can do this with the rest of the possibilities, the right factorization, the left factorization, and so on. The thing is, the flat outputs can be obtained in terms of the states of the system and the inputs of the system. So here you have the possibility of controlling the flat outputs through the state equations and through the input equations. So that's a problem that can be solved. Questions? You tell me what time we should stop.
The zero on the polars has any physical meaning?
The zeros? The zeros.
Zeros on the polars.
And the poles,
Are any physical meanings in multiple variables?
I'm sorry, then.
What are the physical meanings of pole and zeros in multiverse systems?
Okay, yeah, this is a very complex field in which you have all sorts of possibilities for zeros. You have transmission zeros, you have, but the meaning is more or less, intuitively speaking, the same as in continuous time system. The zeros are the blocking of the information coming from the input to the output. That blocks information and the information doesn't go through. Those are sort of singularity points. They might be stable or unstable. But in general, I remember a talk by Professor Sain in which he described an enormous amounts of interpretations for these poles and zeros in multivariable systems. In general, very, very rich theory of poles and zeros. I don't know, probably they'll have some practical utility, but practical and interesting applications, but I have never seen one concrete in terms of an example.
And for this example, this instance, for this example.
Oh, for that example, the poles are determine the stability of the system, and the zeros determine the minimum and non-minimum phase properties of the system.
This is a four-order system.
Yeah.
Why?
Why? Because because we determine that there are, I mean, if you use the differential equations, you will see that it's fourth order, but that might be a little deceiving. You have to compute the pole polynomial. Yeah. And when we computed the pole polynomial for the simplified system, it came to be this. So the order of this polynomial is the order of the system.
If we change the parameters,
everything changes. Well, S cannot be changed. Gamma 2, gamma 1.
If we change this one,
S cannot be changed.
Why?
But S is a complex variable. It's not a parameter to it. It's not a parameter. Gamma 2 is a parameter and gamma 1, not S.
If we change the structure.
The structure is different. I mean, you're talking about different system. That's a different system.
So means the zeros and the polars, maybe they have some common channel.
Possibly, yeah. They had cancellation.
Is the fourth order because they have the same common channel.
Oh no, there's no common channel. The only common channel is it fits two parts of different parts of the system. This channel fits this and this.
Yes.
But this is related to what
have the same structure.
Well, but it's differentiated by this.
Fourth order system.
Yeah, but this is a gamma.
Maybe this is the meaning.
Yeah, so you have four identical tanks.
Yes.
So if the tanks are not identical, then you have.
In full generality, the tanks are not identical. They have different areas and different coefficients. A1, A2, A3, A4. They might be different. We simplify that to identical tanks. But the key issue here is that you have the possibilities of fraction out one of the controls for two tanks. You fraction out it by means of gamma 1 and gamma 2.
You have 4 poles at -1.
Yeah.
And then you impose some structural conditions on these 4 different equations. So these 4 different equations can give you 4 different poles.
Yeah. Well, no, because we equated all of them. We equated all of them.
So that's imposed structure. What he's saying is, if you, in general, this may not be true. That you have 4 different poles.
Oh yeah, but we normalize these things, so to speak. We normalize the time constants to Ti, and so it involves the different areas and the different coefficients and the different equilibrium values for the heights. So in that normalization, and we have a very simplified version of the system in which all we want to exhibit is the influence of these distribution parameters to see how they influence the zero dynamics of the system and the nature of the zeros of the multivariable system. In this case, gamma 1 and gamma 2 determine the nature of the zero dynamics.
So in doing so, you simplify the problem.
Yeah, I simplified the model.
They're all the same time.
Yeah, we simplify the model. They are the same, but nevertheless, you have 4 poles. It doesn't matter if they are equal. You have 4 poles, and the order of the pole polynomial is 4, even though all the poles are located at -1. That's okay, but you have 4. You don't have 1. You have 4.
That's the simplification.
This is the common.
Yeah, they're all common.
The common.
So he imposed the condition. So the problem is it's simple.
Yeah, but look, the coefficients are not the same. Gamma 1 and gamma 2 are different.
So he only wants to investigate the effect of gamma 1 and gamma 2. He can make the speed, the time constant are all the same and equal to 1.
The distribution of the flows different. This is influenced by gamma 2, and this is influenced by gamma. Gamma 1 is a fraction of this flow. It's a fraction.
If we add a pump here,
Oh no.
the constant couple.
No, then you have another control. Yeah,
Not a controller.
yeah. If you,
Constant.
yeah, you're talking about a different system. You only have 2 controls here.
李老师，他这个把这个简化了以后，他就考虑gamma 1、gamma 2这情况。你是说他这个太简单了是吗？太
我是说前面那个定义啊，什么叫基点原理？这个定义它认为是共同的嘛，common 嘛，它叫基点嘛。
对。
为什么会有common呢？因为我下面都一样的。为什么能够到实验中得到都一样的呢？它一定是从同一个点出去一个装置出去才是一样的，从不同的装置出去一定是不一样的。
不同什么地方？
不同的装置信息过去的时候，一定不是一样的。
他这个就是做了一个很大的一个简化，就是一般的情况不会这样。它四个碳都是time constant 都是等于1，它这很简化。
Yeah, even though the system might have the same pole location, look, each transfer function is different.
Yeah.
Each transfer because this is
0.7点有物理意义，我就可以从这个物理现象本身就知道0.7点了，不用推这个方程了。
对啊。
the tanks might be perfectly.
地方肯定是共同的，这个就消掉了。它有不同的共同，肯定多了一个。
几点可以，0点不行。
0点也是通道。
Yeah.
0点是这个矩阵的形式，0点一定跟矩阵的结果有关系。
但是它有共同的嘛？它是common嘛？这个定义里面是common的。如果它没有common的话，它不同的话，它就不是了。
这个0点是一大学问，0点真没有数。它0点有很多种0点，包括这个transmissions 这个是那个以后可以再讨论。不过你说的也对，就是。
You see, each transfer function is completely.
方程去说一个多少0点多少几点，我用方程写偏0点，它就在一块了。但是因为从这个对象本身的物理意义看，它有没有共同的地方
Can you translate, please?
What Professor Lee is saying is, for each device in your multivariable system, the physical characteristic will determine the physical characteristic will determine pole and zeros for each device. So from each device you should be able to tell what are the at least poles.
Well, maybe.
The poles come from 4 different tanks. The pole.
Yeah.
So if each tank has a different time constant, you have 4 different.
Yeah, there is no influence of the gamma parameters in the poles.
Right.
But there is an influence of the gamma parameters in the zeros.
So what are you saying? You don't have to look at the matrix. You just look at each device. You see what the pole is.
Yes. 这才是问题的本质，是描述而已。
You see, even in this case in which you make all the tanks identical, I'm making all the tanks identical. I'm not making them different. Even so, the tanks are identical. You have 4 different transfer functions, one for each tank, and the interaction. Because you have two outputs, 2 inputs, and the inputs are interacting with all the states. So even though the tanks are identical, the transfer functions are different. You're right in the sense that the poles don't depend on these coefficients that determine the fractional amount of flow going into 2 tanks with respect to the other 2. Those coefficients might be 0.5, and then you will have 4 identical transfer functions.
So gamma 1, gamma 2 describe the interactions. I mean, the numerator describes interactions among different channels.
And not only the interaction, but each particular.
The pole locations are determined by
yes.
individual tank.
Oh yeah, but here they are all the same.
Well, that's your assumption. But in general, that you have 4 different tanks, 4 different constants.
Oh yeah.
4 different.
Yeah, surely, but there is no discussion about that. But you have, I mean, it's kind of complicated, right? Right. This is a nonlinear system. All these coefficients are different.
但是我的印象里边，那个 transmission zero 是跟其他的东西有关系。
Yeah, those things will not affect the zeros as much as the gammas.
因为这2个 channel 可以互相消反，对呀，消一个消，这2个 channel 之间的关系。
就是明显的。
对。
这是从一个对象本身看出来的。
That might be important. But the issue here is not that. The issue is to see what these innocent-looking parameters determining the ratio of the flows into the lower and the upper tanks in an intermixed manner. What is the influence of those things in the internal stability of the system? That's our main objective here. The tanks might be essentially equal, identical. That doesn't matter. What you obtain is that only in one particular case the transfer functions will be different or will be the same. When gamma 1 is half and half. Half goes to this tank, the other half goes to the other tank. And the other has half and half distribution parameter. In that case, the 4 transfer functions are very much the same. These 2 are the same and these 2 are the same. Will you speak in English? Because you're talking, I want to understand.
The gamma 1, gamma 2 is only for the controller, the different ratio.
Yeah, it's the influence on the zero dynamics of the system. Yeah. And the zero dynamics determines a lot of things.
The flow of the output, the tank is different. For example, maybe there are some other functions inflect the flow of the water. So the poles are different.
Yeah, but that doesn't change the nature of the zero dynamics, which I'm interested. We're looking at minimum and non-minimum phase systems. If I ignore the influence of gamma, I will not find anything. But here, of course, you're right. You will have 4 different parameters. But the most important case is the one in which you have more difficulties. Even though the tanks are exactly the same, their internal dynamics is not determined by the geometry of each tank. It's determined by the ratio of flows that flows from the upper to from the lower to the upper tanks.
So can we say in multivariable system you are more interested in the interactions among different channels?
Of course.
And that's what the zeros represent.
Yeah.
Right? So gamma 1, gamma 2
are the parameters that define somehow the stability. Excuse me. Hello, mi amor. Let's just see these two next slides, and we'll leave for the next lecture the state space representation. The other representation for linear multi-input, multi-output systems is so-called the polynomial matrix description, and in this case you have something similar to state space representation. You have sort of this is called actually the pseudo state. The pseudo state multiplied by some polynomial matrix, and the control multiplied by another polynomial matrix, and the output of the system being a combination of inputs and outputs. This is a different representation, very similar to the other one, but the input-output representation goes through an intermediate state called the pseudo state, and the pseudo state is C. And this system is controllable if and only if D and N are left coprime again. Because if this is controllable, then it means that C doesn't satisfy any differential equation by itself, and therefore the output, let's say, is well defined, in a sense. And now the problem is, to control this system, the problem of controllability is ascribed to the input to state representation. So in this case, it will be input to pseudo-state representation. Remember that the flatness is a property between inputs and states, whatever they represent. And in this case, the pseudo-state is the closest thing to a state. In the single input, single output system, what is closest to the state is the proper definition of the flat output, which is a dynamics with no zero dynamics and controllable canonical form. So that sort of says that the controllability of the whole system is ascribed to this input to pseudo-state representation. So D and N have to be left coprime. So in that case, it would be natural to see if this intermediate variable can qualify as the flat output, and because it's an endogenous variable, it's inside the system. And so the vector qualifies as a flat output if and only if three conditions are given. First of all, the system is controllable. That means that D and N are coprime matrices. Second, the dimension of C equals that of U. So that this is a square system. That's very important. And then the other one is that N has to be unimodular. If those three conditions are satisfied in this representation, then the system is flat. And the flat output is C.
You said it's non-squared. M input, P output.
Okay, in general, you have, M inputs, but you have M Cs. The outputs are C. These are the outputs. These are not the outputs.
P output.
They are the same number of the dimension of C is equal to the dimension of U.
But the dimension of output is not.
It's not equal.
Right. So
It doesn't have to be. Yeah, the system is not square from the input-output, but it's square from the input to the pseudo-state.
Okay.
That's the square system. So the dimension of C is equal to the dimension of U. And the output can have a different dimension. Remember, the controllability properties are ascribed to this description of the system. And in input-output descriptions, you have no choice. There is nothing like that. And you're stuck with that particular form. So if these three conditions are satisfied, the system is flat, and C is the flat output. That's very useful when one has troubles obtaining the factorizations, because you can take out the outputs independently, dependent on inputs and outputs, and try to build a subsystem here which is square and which has these properties. So as an example, here you see one output, two inputs. This is a non-square system, and you have U1, U2, and you have C as your output, your actual output. So what we look for is a square representation in terms of a new vector C with two components, so that it has the same number of components of U1 and U2. So first of all, what we do here is we reduce everything to a common denominator to obtain this representation of the output in terms of the inputs. That's a non-square system because you only have one output and two inputs. But if you define C1 and C2 is a pseudo state, which somehow takes advantage of this possibility and lets the inputs go through a single channel, then C will be able to be represented in terms of that C, because this factor is there and this factor is there. So C will take somehow this form. C will take this form, this times this, and C will have two inputs and you will produce two outputs. So this is the natural definition, and the representation is in pseudo-state representation with an identity matrix here and an identity matrix here times this factor, which is a rational transfer function matrix representation of this part of the system which is square, and the non-square part related to the pseudo-state is governed by this relation. So now we have that these two matrices are coprime. They don't have any common factor except the trivial factor, which is the identity matrix. That's trivial. So these are coprime. This has the dimension of this, and this matrix, because you can put always this matrix there. This matrix is what? Is unimodular. So this is the flat outputs are C1, C2. They're directly related to U1 and U2. And C1, C2 differentially parameterizes the input because this differential polynomial can be put to affect the two of them. So U1 and U2 has a differential parameterization. And since that is the case, C will also have a differential parameterization in terms of C1 and C2. So that system is flat. And now we get to the state representation. I prefer to let that for a next lecture, because that is the most important case. The other cases, you can the physical meaning is not so clear. That's true, and but it is useful to know that in those representations the zero dynamics is very well hidden, and in order to extract it you have to know about the poles and zero definitions for this class of systems. And this factorization is not always easy to obtain, so in practice, you brought them, thank you.